Thank you. And thank you, researchers. It's really interesting to hear. I think as a social scientist that does a lot of work in integration of science and tech in society, we're always thinking around that role of, what are the unintended consequences and trying to tap into those early. And I was thinking about this, in preparation, and obviously former Chief Scientist Dr. Alan Finkel did a lot of work in some of the early studies. And one of the things that came out towards the end when he was at the Human Rights and Technology just after that, one of his words of warning were that in this new age of artificial intelligence, our key challenges is to harness the power of science to enhance human lives without sanctioning practices that violate human dignity. And I think that's really endemic in what we're seeing being presented today. I'm just interested, if we think about trust, I'm going to just ask you quickly, who uses Siri and has it turned on their mobile phones? Put your hand in the air just to see. Who uses Google, like ask Google, okay Google? So not even half, perhaps? And we're an educated group. I'll leave you to ponder that as we think about going forward. So I have the very good fortune to introduce our keynote speaker, so bear with me because he's very esteemed, so we have a bit of a bio here. Dr. Vishal Sikka is the founder and CEO of Vyani Systems, a human-centred AI platform and products company launched in 2019 to address the unfulfilled promise of enterprise AI. Based in Palo Alto, California, the company is backed by many of the most influential investors in the industry, has a rapidly growing customer base, includes a leadership team with unmatched expertise in building breakthrough products and delivering customer success. Nimrod from UQ Ventures would say that ticks all the boxes. Dr. Sikka serves on Oracle's board of directors, the supervisory board of the BMW Group, the GlaxoSmithKline board of directors, and the advisory council for Stanford University's Institute for Human-Centered AI, and also served as the co-chair of the World Economic Forum's Council on AI, which I know has had a profound impact and influence across the world. From 2014 to 2017, Dr. Sikka was the CEO and Managing Director of Infosys, a $10 billion plus revenue global technology services company. As the first non-founder CEO of Infosys, he led the company through a generational shift in a time of significant changes in the services industry. Changes brought on by cost pressures and the rapid advancements in technology. And he implemented a renew plus new strategy that helped clients renew their existing IT landscapes to drive down costs using automation, while simultaneously bringing breakthrough innovation using design thinking and next-generation technologies like artificial intelligence to transform their customer experiences. Prior to Infosys, Dr. Sikka served as a member of the executive board of SAP SE, leading all products and technologies, including driving all product development and innovation globally. During his 12 years at SAP, he was instrumental in bringing a culture of innovation and intellectual renewal across the entire company. There's a theme coming through here, isn't there? Dr. Sikka is credited with articulating the principles of timeless software and creating SAP's breakthrough in-memory data platform, SAP HANA, the fastest growing product in SAP's history. Dr. Sikka has a distinguished background in the field of artificial intelligence. His PhD was in AI from Stanford University. Professor John McCarthy, known as the father of AI, was the head of his qualifying committee. He's an adjunct professor of computer science at East China Normal University, Shanghai, and an adjunct professor of computer science at Stanford. In 2016, Vishal received an honorary doctorate from UQ. And in the citation, our Chancellor described Dr. Vishal Sikka as a globally recognised innovator and business leader who champions the transformative power of technology to amplify human potential and address extraordinary global challenges. Please welcome Vishal. Thank you.
Thank you so much. That was quite a handful. My talk today is about none of the business stuff that I have done. It is about AI, and I've been involved in AI much of my life, adult life. I did my PhD at Stanford I studied, as an undergraduate student at Syracuse, I studied computer vision back before CNNs and the examples that Shakes talked about. There used to be the whole paradigm of model-based vision and so forth. And then I did my graduate studies at Stanford, and in between, I had an opportunity to spend a memorable summer in the AI lab. This is 1990, in the AI lab at Intel. And I studied neural networks that were being built there for the use for in predictive maintenance of the manufacturing line at Intel. And I saw today some examples of predictive maintenance of machines using neural networks. And then I did my PhD in the kind of AI that was prevalent in those days, which was symbolic AI. And so I have had, over the last 35 or so years, this unique perspective on multiple generations of AI. And I thought, when Shazia asked me to come and give a talk here, I was thinking about, what will I share with such a diverse group of people? And obviously, many of you are distinguished researchers yourselves and so on. So I thought that at least in the Northern Hemisphere, it is summer season and it is reading season. And a lot of people ask me, what are you reading? And one of the beautiful books I happened to run into recently was a book called 7 Brief Lessons on Physics by Carlo Rovelli. I know it is winter here, but if you happen to find yourself some time to read, this is a very nice book with 7 short lessons on interesting aspects of physics. So I thought I'll call my talk 5 Brief Lessons on the past, present, and future. So how do you condense 35 years of personal experiences into 35 or so minutes? So we'll give it a go. So 5 brief lessons, not a big deal. Lesson 1, I'll try to do this in 5 minutes each or so. We'll leave 10, 15 minutes for questions and answers. AI is an old field with some very impressive recent results. One can argue that AI has been a sort of a fascination for humans for millennia. Starting in the 50s, 1956, John McCarthy and Marvin Minsky and a few others did this summer workshop at Dartmouth, where they thought that a new field was needed. John McCarthy came up with the name artificial intelligence, Minsky gave it the definition, and a field was born. Minsky's own thesis was on a very, very early variant of neural networks, something that he had built at Princeton called SNARK. He used to have this transistor tubes, vacuum tubes based SNARK thing in his office at MIT when I studied there with him briefly. But basically, if you think about AI in these epochs, students of AI will tell you there were many and so on. But basically, you can say that there was AI up until roughly 2011, and then AI after 2011. It's a simpler, good way to think about the two sort of generations of AI. Up until 2011, bulk of AI was the symbolic paradigm. I have 2 pictures, one of an expert system called Mycin. Unfortunately, it is not very clear. You can look this up, of course. On the left-hand side of the Mycin picture are these rules that Mycin had. Mycin was a system that was built to do medical diagnosis. And it had a whole knowledge base of rules around how doctors make their decisions. So, if you want to predict if a person has the influenza or whatever. And the thing on the right of that picture is the reasoning tree of Mycin. So the thing about it was that, yeah, it would tell you if it thought the person has, based on the symptoms that it could see, the flu or not. But it had one of the researchers was talking about explainability. So this was fully explainable. Every aspect of what Mycin diagnosed could be traced back, and it would generate a whole tree of how it made that decision. Even before Mycin, there was a system that Josh Lederberg, who was a Nobel Prize-winning chemist, built together with Ed Feigenbaum called Dendral. And that was, recently there was news of DeepMind building this protein folding thing, which I'll talk about briefly later on. Dendral was one of the early chemical expert systems that predicted the 3D molecular structure of molecules. And here there is an example of those molecules and the rules around that. So this led to a lot of interesting applications. Of course, for these decades, AI was viewed as quite an exotic field. A lot of research went into it, a lot of funding went into it. Nothing really breakthrough came out of it, although AI applications were pervasive. I have a nice picture there of what is considered the best rice steamer in the world. I'm told Wasim makes very good biryani. But this Zojirushi Neuro Fuzzy rice cooker has 26 fuzzy logic rules in it that make the perfect pot of rice. Of course, AI back then also had its series of hype. Herb Simon, who was one of the pioneers of the field, an incredible scientist, won the Nobel Prize in economics. In addition to pioneering work in AI, even he got caught in the whole hype back then. And in 1965, before I was born, he predicted that machines will be capable within 20 years of doing any work that people do. Of course, we haven't been even close to this. So if I could take these decades of this pre-2011 work and put it in a very unfair nutshell, I would say this work was governed by representation and reasoning of real phenomena, modeling that phenomenon and representing that in ways that are machine interpretable, and then reasoning about them. Everything that these systems did was fully explainable, was fully verifiable, but the systems were painful to put together. I remember when Ted Shortleaf, who was the architect of Mycin, he was one of my PhD committee members, he used to say that they would ask doctors how to do their diagnosis, and doctors would very earnestly tell them painstakingly how they reached the diagnosis. And yet the diagnoses were inevitably wrong. This was called the knowledge access problem in those days. And I always used to wonder, why that is. And ultimately I found the answer in Tim Galway's book called The Inner Game of Tennis, when he said that the parts of our brain that play tennis are not the parts that speak English. And so this particular AI never quite broke through. It was because of the inaccuracy as well as the inefficiency problem. If we fast forward to the last 10 years, 11 years, of course, the hype has sort of reached a whole different stratosphere. Google CEO compared AI to fire. Andrew Ng compared it to the new electricity. Harari got into the act, called it a technology that will create a useless class of humans, and so on. Some of this is, of course, when you read the headlines, somewhat justified. This box in the middle that says squad on it, this is today's leaderboard of the squad benchmark. Anybody here know what squad is? Squad is the Stanford question answering data set. This is the second version of it. It's similar to the SAT reading comprehension kinds of problems. The difference, of course, is that the reading comprehension problems here are self-contained, meaning the answer that you're looking for of a paragraph, Napoleon invaded something, and then you ask questions about what Napoleon did. The answers are inside the paragraph itself. So you don't have to have this ability to understand have common sense or understand how the world works in order to answer these questions. The answers are inside the paragraphs. The interesting thing about this is that they had a sort of a human benchmark, which was done on a service on Amazon called the Mechanical Turk. So 500 or so humans got together, read these same paragraphs, and these are not experts in language or anything, just normal people. And that established a baseline along two kinds of tests, and then they measure that. This is the second version of the benchmark. Basically, if you zoom in on this picture, and you can go to Squad leaderboard and see this yourself, all top 20 systems now beat human performance. And I think 16 out of the 20 are in China. The other 4 are from other parts of the world. The reason 2011 is a somewhat significant event in the history of AI is because of the invention of a system called AlexNet, which broke open the field of computer vision. For the first time, a computer vision system beat the human performance on ImageNet. ImageNet is a database of images that was built by, led by Fei-Fei Li, who's at Stanford. She's the co-director of the Human-Centered AI Institute there. AlexNet created quite a sensational ripple when, on recognition, image recognition tasks, a system for the first time beat human performance. Now, this is the picture from last month. AlexNet is sort of the second dot from the left. There are about 400 systems that perform better than AlexNet. Last month, quite an extraordinary thing happened. Last year, you may have heard about this thing called AlphaFold from DeepMind, a division of Google. They did, for the first time, this 3D folding. Whenever a medicine for a disease, for example, is basically a protein that attaches to a disease molecule in some way. And so predicting the shape of these molecules, drug molecules, protein molecules, is quite an important problem. And they did that, and that was a very significant advance. Last month, they sort of took that to a whole different level and predicted the shape of basically every protein that is known. So now this elevates the science in quite a significant way. And there is reports that we read about AI writing college papers. I was very happy to see here some work on dermatology that is happening here and in medical imaging and so on. In particular, in radiology, there is quite a significant change that is happening as a result of AI. And one of the things that I'm very encouraged by is that the Society of Radiologists has made understanding machine learning an important part of the curriculum for radiologists. And I think that so that they understand what is happening in the field. So quite impressive results, you can say. Some more examples here, using something called generative adversarial networks to generate realistic human images. None of these people is real. These were all generated by people. You can see that the ability of AI to generate artificial human faces has become really, really good. And in the bottom right is Kendrick Lamar, a famous hip-hop singer, who recently, his most recent song uses deepfakes to morph the pictures of other people onto his own face in a way that is really indistinguishable from reality and quite creepy, if I might say so. Game playing has become, AI systems have become so good at game playing that basically there aren't many games left where humans are better. We all know about Go and chess and all of that. Even on multiplayer games, you see these things. And on the bottom left, I have some examples of image generation using AI, including bizarre images like these teddy bears mixing sparkling chemicals as mad scientists in a steampunk style. Okay, so enough of that. We admit that there are very impressive things going on here. There is also quite an astronomical rise in the computing that has gone into, that is going into AI. I have these graphs. They're all log scale graphs, compute data sets and parameters in these networks. And they are all increasing actually faster than Moore's law, all of them. And as a result of all of this, also there was this Google model called Minerva, which was applied to high school competition mathematics on the math data set. And it is now performing at about the average level of a high school student. Okay, so I promise that was the end of the scary part. So we can say that the first point I wanted to make was basically that there were these two epochs in AI, all produced interesting results, but just really in the last 10, 12 years, the field has broken open and a lot has gone into it. As a result of all of this, the second point I want to make is that AI is seeing a very massive but also asymmetric investment and adoption. In my work, both on the boards as well as in my own company, we studied this. And this itself is a field of study, and one of your colleagues talked about the work with KPMG on trust. My sort of, again, in a nutshell, summary is that there are 3 tiers of organizations in terms of their AI competence and AI sophistication. Roughly, there are 20 companies, big companies, mostly in the US and China, that altogether spend about $200 billion. And I put all the zeros there just to make the point. Because in our brain, million, the word million and the word billion have the same number of letters. So it's like a million, billion, trillion. But a billion is 1,000 times bigger than a million, and a million itself is a pretty large number. So it's $200 billion a year between these 20 companies per year. Given that the technology is increasing in its capacity exponentially, so every 2 years, you basically get a computer that is better than twice than it was 2 years ago. And these companies make massive use of AI models. Even just an iPhone has dozens of models in it just for the phone's operations. And Apple isn't even the top user of AI of these companies. It's companies like Google and Facebook and the big Chinese companies and TikTok. TikTok, for example, builds several models for every single user. So in TikTok's, I'm on the board of Oracle, and if you remember in the Trump administration, there was this drama going on around making TikTok an American company and all that. So we looked into it. There are about 2 billion models that TikTok has that they run continuously. At the second tier, there are sort of these 200 or so, I don't know exactly how many, but roughly in the neighborhood of 200 industry leaders. These are people, you would put Tesla in this bucket, Netflix, Airbnb, companies like this, which are not themselves technology companies serving technology to other people, but they are tech first, meaning they are sort of reinventing some domain or the other using technology, and they make pretty significant use of AI as well. You could argue that these are companies where their core business depends on running AI. And Netflix, for example, could not operate without AI, or Airbnb or companies like that. So they use AI massively in their core and operational areas, but not nearly in the same league as the top 20 companies. And then basically there is everybody else. And everybody else, every company that I talk to has something or the other going on in AI. Generally, they are in early stages, doing some AI projects, hiring some data scientists, have some early processes in place, are not aware of the issues around AI and so on. And basically, and the speed at which this stuff is becoming disproportionate is quite incredible. I started my company in 2019, and in the last 3.5 years, every assumption that I started my company on has in fact become even more asymmetric instead of coming back towards a convergence. So that was the second point, is the asymmetry of everything. And it's difficult to overstate how big that asymmetry is. But the third point, and here is where our work plays an important role, is that AI today has really fundamental issues. Here are some headlines. One category of issues is around bias. There are some examples. The graphs there are Amazon applied AI to they celebrated that they were going to hire people, because Amazon hires a lot of people. I think they have more than 1 million employees now. And they were going to use this fancy AI system to hire. And it turned out that the system that they built was really disproportionately bad towards minorities, especially towards African Americans, and especially against African American women. It was like 10 times worse on hiring, because basically the company had never hired African American women. So the examples that they had in their data sets did not have the right mix of people or the right mix of priorities that the organization needed to have. And as a result, the AI simply reflected inadvertently the priorities of and the principles and the processes of the organization, and you had this result. This is everywhere. I think one of your colleagues who spoke earlier talked about this AI system that was recognizing X-rays from whether the people were already on were standing up or functioning when they were taken, when the X-ray was taken, or versus when they were already on a bed or something like that. There is a particularly drastic example of that. One of these dermatology AIs actually was zooming in on the markings on the X-rays, and those markings were placed by people who suspected that there was cancer in those X-rays. And so, of course, the thing about it is that these deep neural networks, they are trained on large amounts of data. And so the basic mechanism is that this deep learning using neural networks, you give it a large number of samples and say, these are the things that have cancer and these don't have cancer. And then it learns and it minimizes the distance between where it is at and things that have cancer, and minimize the distances between where it thinks there is no cancer and the ones that don't have cancer, and so on. And before you know it, it has trained itself into doing this thing better than humans do. Except it may have got there by looking at the wrong things, because it actually has no idea about what a marking is versus what a cancer is, or which part of the image represents cancer and why, and so on. Another stark example of that is a Google, that turtle on the right-hand side. The reason that red thing is mislabeled is it actually thought this was a rifle. For some reason, this turtle looks like a rifle. And if you ask a person, even a child, is that thing a turtle or a rifle? And they're like, it has the flaps and it has the shell, and the shell is a different color than the flaps, and there are 4 legs. It's a turtle. These AIs have absolutely no idea about how to break these kinds of things down and explain why. And so the work on explainability that you heard about will tackle these kinds of issues. What is it that when we give an explanation for something, why do you think there was fraud in this transaction? Or why do you think this particular machine is going to fail? You have made us stop all of this. What is your basis for this? There has to be an ability to, and I have a few more examples here. The stop sign thing was particularly interesting. Some of these research, this was done by Tencent. They were able to fool an AI system into believing that the stop sign was actually a speed limit sign by putting certain markers at the right spots in the images. So you can see that there are these black and white stickers that were put in there. And they were enough to trick the system into believing that this was in fact a speed limit sign. Now again, if you ask a driver, would they ever confuse a stop sign, even if it was a Turkish stop sign or a stop sign in China or something? Would be like, no, stop signs are octagonal and they have a red thing and a white thing, and speed limit signs are white rectangular things with numbers inside them, and no, this is not a stop sign. But that's sort of where we are at. I'm on the board of BMW, and autonomous driving is in one of these really particularly affected by this hype and lack of understanding what AI is. Finally, last month, or in June, they analyzed something like 400 crashes that have happened in the last 2 years because of these partially autonomous or ADAS systems. And 70% of those involved Teslas. Not because Tesla software is particularly bad or worse than the others, just because more of Teslas have them, and the autopilot, whatever they call it, is always active or something like that. So it's used more prevalently. But nonetheless, 70% of the semi-autonomous crashes, including fatalities, happened on a Tesla. And there was this one particular incident where, while on autopilot, there was a crash and a person died. And it took the authorities 2 years to figure out. Of course, the driver blamed the autopilot system. But finally, the authorities charged the driver that, yes, it happened. And this driver was apparently had fully reclined the seat and was watching a game or something. And when the car crashed into this person. And the authorities found that it was, after all, his car. And yes, the autopilot was engaged, but the human is responsible for the car. So it is, and in there lies a very important lesson for how these AI systems need to serve us. Recently, this thing became particularly, this hype became particularly acute because a Google engineer gave an interview where he said that, I think this AI has become sentient. I happen to understand what these large language models do, and I thought this is complete nonsense. What are they talking about? Actually, cynically, I first thought that this was some kind of a marketing gimmick, that they were saying that this was like a very smart ploy by Google to say that their AI has, their own engineer believes that the AI has somehow become sentient. It turned out they fired this guy a couple of weeks ago. So what is going on in here? And I want to give you for those of you who don't know this stuff, I want to give you a 3-4 minute, very, very quick explanation for what is going on here and why this Google AI is definitely not sentient. There was a extension made to the technology of deep neural networks with a mechanism called attention. So let's say I told you that I have this really cute dog and he loves to play in the snow or loves to play when I get back home. When you say he loves to play when I get back home, the he is referring to the dog. So this reference is very common in language. So to figure out the way of capturing these references, some scientists invented a technique called recurrence, recurrent neural networks, or with a thing called LSTM back in the late 90s. So this idea of capturing the reference of words and adjectives and so forth became bigger over the years, and a mechanism called attention was written about a few years ago. And then that attention mechanism took the shape of a particular function inside these neural networks called transformers, which basically have the ability to take a sentence and transform it by accounting for these references to past occurrences of other things. So this is basically the core invention beyond the basic idea of a deep neural network. So on this transformer idea, and a few variants of this transformer, whether it is forward directional or backward directional or both, a bunch of, and these are some systems that have been built like this. The most successful one of these, which broke open the field of language processing, summarization, language translation. So when you use Google Translate, these are the systems that are being used. Or the squad that I told you about earlier, beating human performance in reading comprehension, these are the systems that are basically being used for that. BERT, which started this just 4 years ago, had 108 million parameters inside it. The large version of BERT had 3 times as many. Then Google made a system in 2020, 2 years later, which had more than 10 billion parameters in it. OpenAI did a thing called GPT-3. You may have read about GPT-3 and how it makes these remarkable summaries and all of these things. Basically made it even bigger with 175 billion parameters. 175 billion parameters. The neural networks that I worked on in 1990 had like 10 parameters. So this is 175 billion parameters. Um, Training from scratch a 175 billion parameter transformer model costs about $35 million. So right there, any organization that cannot afford this kind of a thing is basically out of the of this particular game. And of course, these big companies, Microsoft and NVIDIA together did this MT-NLG, this Megatron next generation language something NLG, with a 530 billion parameter model. And Google made the biggest one of these last month, Palm, which has 540 billion parameters. So these things are getting ridiculously large, to put it mildly. And inside there, I already mentioned this to you, is basically, if you take the time, it takes about a day and a half to understand what a transformer is, how it works. If you get a good introduction to it, it's not mysterious. It is a way to understand large amounts of sentences and figure out how to predict the next word that you are about to speak. That's it. It is a very elaborate, very complex function to predict what the next word is likely to be. And then you can use it to complete sentences. You can use it to fill in an empty word in a sentence. You can use it to produce pictures. That's a different thing. You can get into that in the Q&A if you want. But that's basically what it is. It is not sentient. It has, in fact, no idea what it is talking about. It has been trained on vast corpora of books and Wikipedia pages and all of this stuff. It actually doesn't know what is truth and what is fiction that it has read. None of that. It is a technique to fill in sentences with words, predict the next word, or fill out an empty sentence. And there is an example back there of how this specifically works. Udaya Pearl, who won the Turing Award in 2011 for his work on causality, called this curve fitting. And I think it is, in his wisdom, he captured it exactly right. That the deep neural networks, the 540 billion parameter models trained on every word that has ever been written by humanity, in the end are simply fitting curves on the data that they have been trained. John captured it in a more eloquent way a few years before. Towards the end of his life, towards the end of his career, he started to get into machine learning to see what was going on there. And after a few years, he worked on a project called phenomenal data mining. And his point about phenomenal data mining was that not just phenomenal data mining, but data mining about phenomena. And his point was that machine learning focuses on an appearance. But there is a reality behind the appearance that causes that appearance. And that reality follows laws and it follows principles and there is dynamics of it. You have to try to understand what that reality is. The entire purpose of science is to understand that reality behind the appearance. That, oh, there is a wobble in the orbit of this star. There must be another star that we cannot see that is hiding behind there. There is this shadow falling here, and there must be the sun on the other side of it, even though I cannot see the sun. We can reason about things like this because we understand how the phenomenon work. And I think until we develop AI with these abilities to understand the phenomenon behind the appearance, the reality behind the appearance, we will have an incredibly powerful appearance machine, basically. So, this lack of understanding the reality behind the appearance manifests in the form of these issues of bias and meaning and opacity. And these issues have to be solved. There is also a massive talent asymmetry. So Jeremy Howard has been hanging out here he works on fast AI and so on. I don't want to get into this. Let me just say that back in 2018, Tencent did an analysis of how many data scientists there are. At the time, their estimate was there are about 300,000 AI engineers in the world. 300,000, that's it. And out of those, about 20,000 were people who could actually explain AI technologies to you. That number has probably grown by 3x in the last 4 years. My own estimate is that there are about 1 million data scientists in the world now, AI, people who could build you an AI system if you wanted to look at the faults on a road and say, hey, can you predict when there is a fault or when there is no fault? About 1 million people like this, out of 7.75 billion people on the planet. 1 million. And the cost and performance I already told you about. So we need a better way forward. A way forward that is based on trust, that is based on a vast simplification of this, based on verifiability, not just, so by verifiability I include explainability, interpretability, the ability to understand what is going on, why do you think I should make this decision, why do you think there is cancer here, why do you think there is fraud here, and pervasive access and education. I think enterprises, whether they are the advanced ones talk to us primarily about limiting the costs now. Even huge companies like Facebook worry about the costs of training systems. The middle tier that I talked about, they worry about cost and performance as well as some of these issues around regulatory compliance and so forth before they hand over important decisions to AI. I think universities, I'm very pleased that the 4 talks that you picked, Shazia, 2 were about AI techniques and 2 were about AI techniques. And I think that is very important. As much as we try to move forward on the techniques themselves, we should also move forward on the brackets around the techniques, the explainability, the trust, and so on. And I think there are some government people here. I think that developing an understanding of AI, developing a framing for AI is something that is extraordinarily important for our times. We have done this before. Nuclear technology was one of these dangerous technologies. And by and large, with the exception of 3 accidents in the last 75 years, we have managed to use nuclear technology. We have managed to regulate it and keep it. There haven't been explosions, knock on wood, so far. There haven't been accidents other than those 3, Fukushima and Chernobyl and 3 Mile Island. We know how to do this. We know how to get ahead of difficult, complicated technologies. We have to do that with AI. My own company, I believe that we need these. So we work on applications, applying AI, this kind of human-centered, explainable AI, trustworthy AI, simple AI, to applications for different industries, for different kinds of areas, as well as a technology platform, an open technology platform, a cloud-independent technology platform that can help enterprises develop this kind of causal, explainable, reliable AI that optimizes on cost and so forth. But anyway, I don't want to get into this. This is just a quick introduction. If we do good AI, of course, the applications of this are enormous. Every walk of life, everything that an enterprise does can be transformed using these abilities. We know that there are thousands of startups. It's one of the most active areas of investment in venture capital. But I want to close, I want to close with a few perspectives. One of the first things when I joined the board of BMW that I was asked was, when are we going to have an autonomous car? And I told them that not in our lifetime. And they were like, what? Elon Musk says we'll have it in 2019, like this year. That was 3 years ago. And I said, no, we are not. No matter what Elon Musk says, we will not have a car that drives itself in any unconstrained situation, what you call L5 autonomy. We will not have this, not for the next 50 years. L4, what people don't realize about autonomous driving is that L4 autonomy, which is about instrumenting the infrastructure, the road, this we will have within this decade. We already have some examples of this. But then we have had various examples of L4 autonomy. The people mover at Sydney Airport, or all the trams that go up and down Swiss mountains without a driver. We already have L4 autonomy. So there is a vast difference between L4 and L5. Just like that, there is a vast difference between being able to read a paragraph versus being able to understand the meaning behind that paragraph. And people focus on this general intelligence and human level intelligence. We are nowhere close to that. We don't even have the techniques to solve these issues. Once we have those techniques, which will take decades, then it will take decades to bring those to life. So I would not worry about stuff like that. I just want to give you one particular dimension of this, which is, there is this mad race, the 540 billion parameter model and all this. We have about somewhere between 10 to 100 billion neurons inside us, nerve cells. And every nerve cell is connected to about 10,000 other nerve cells on average. So that means we have somewhere in the neighborhood of 100 trillion to a quadrillion synapses inside us. And a long time ago, Carver-Mead did this analysis. And people used to think that when we have 90 billion transistors, we will have an intelligent computer. Back in the 90s, people used to think that. And then 90 billion transistors came and went a long time ago. Nothing happened. Now there is this race to get to 100, now this year there will be a 1 trillion parameter model, and then, people are trying to get to this number. But the hyperparameters in a deep neural network are not the same as synapses. It turns out, this is a paper from earlier this year, they found that within a single synapse, we seem to have the ability to do computation. A synapse, based on a particular experience, could wire a memory into the genetic structure of us and have it be remembered across generations. There is a Turing-complete mechanism inside every single synapse. So we should not worry about things like that. The Google AI is not sentient. On the other hand, perception and understanding, we already have incredibly powerful technology to do that. What does that mean for us, and how can that amplify us? I think this is the fundamental issue. Intelligence emerges from pieces that may not themselves be intelligent. Alan Kay says the music is not in the piano. And AI to amplify our judgment is what we need to do by using this vast ability to perceive and to understand, so that it can amplify our judgment, so that we can see a lot more than what our eyes can see, that we can process a lot more information than we are biologically able to comprehend. I think that is fundamentally the point. But then doing that means that we have to design these systems for human consumption, and this, it turns out, is a very deeply designed problem. Back in 2013, I came here, we set up the Center for Design. This is the fundamental issue in designing intelligent systems, is the humanity of it, not so much the AI of it. How many of you know what this is? You do? Some of you know what this is. So about halfway between here and Adelaide, there are these structures on this river. This is the Barauna River. And these are fish traps. And so when the tide is high, the fish get trapped inside. They'll strategically open one or two of these rocks. And when the tide is low, the fish get trapped in it on the other side, coming in from the other side. These traps were made, the common consensus is that these have been around for the last 30,000 plus years. Right? Yeah, for tens of millennia. And I find something very deeply moving about this. It was a gathering place for many different nations, many different families, tribes to come together. We talk about the traditional owners, and I always find it really impressive when I come to Australia that every talk, every substantive gathering starts by thanking the traditional owners. This is what they built. And is this an intelligent system? Of course it is. It is a system built out of rocks on a body of water. And it is a very, very early example of how tools amplified us, how they improved our ability to be bigger than us in a very human, very sustainable way. These are still there on the river. If I have time on Saturday, I'll go there. I think, in a sense, AI is no different than a new kind of a fish trap. It can be, if we apply the same care and the same kind of rigor and understanding and humanity to it. It can be just another one of these amplifying technologies. They used to teach children to go in there and pick up the fish because the fish were in there. And then they would release the rest that they did not need by opening up the rocks on the other side. So 5 points, an old field with very impressive recent results. As a result, is seeing massive but asymmetric investment and adoption. Has many fundamental issues that need to be resolved. We need a better way. And with that approach, it can be a great amplifier of our humanity. Thank you very much.
Thank you very much for that, a really insightful sort of lesson as we move through this development. So I appreciate it. I really loved your last sort of point there about the amplifier of humanity, because I think reading back over some of these things, there's this discussion around attached to every AI type thing, there should be a decision maker somewhere responsible for it. And I think about the Elaine Herzberg, the first person that was actually killed by an autonomous vehicle with Uber. And it was all to do with, she had a push bike, and the person who was actually trialling, as you say, was actually on her phone and not actually monitoring the trial, and the unintended consequence yet again. I'm going to just open up because I'm sure there's lots of questions. So let's have a couple of questions, and then we do have afternoon tea and there will be more time to interact. But does anyone have a burning question that they'd like to ask? There is a microphone, so if you wanted to put your hand up, right there, perfect. And please stand up and introduce yourself for Vishal. Thank you.
Hi, Vishal. Fantastic talk. Thank you so much. Pankaj Shah from the Queensland Brain Institute. I was interested in your last slide there. I was just wondering what your thoughts were about using the findings that are coming out of computational neuroscience today, where people are thinking about exactly how computations take place and the kind of, and it was interesting to see the 25 watts you had there, which you didn't mention. The amount of energy that's consumed is tiny, really. And how you thought the interaction should work.
Yeah, the 25 watt thing was, we basically, with that 250 trillion synapses, we get by on about 2,000 calories. In many cases, even less than that. And that's about a 100 watt light bulb on 24 hours a day is about 2,000 calories. And of that, the entire nervous system seems to take about 25 watts. So that's what we operate on. So this is, if you're doing the math compared to the modern computers, that's about between 8 and 9 orders of magnitude more efficient than today's computers. So between 8 to 9 zeros still have to be removed from this equation. So this will take a long time. I think that there is that field, computational neuroscience, there's a very active field of trying to understand how our learning and how our cognition and all of these systems work. I think that can inform a lot about AI. I think AI research does not have to be limited to understanding how we work, but obviously we are a reference that it is possible to construct a machine, quote unquote machine, that can do these kinds of things. One area that I am particularly curious about is Hebbian learning. It seems to be clear that our brains don't do backpropagation. which is the current paradigm in deep neural networks. So yeah, so I think that is a very needed set of work that needs to be done. I also think one thing that I really appreciate about what you are all doing here is the cross-disciplinary nature of it. That is also something that Stanford learned in the human-centered AI work, is bringing together disciplines. Not that the computer scientists become technicians for the domains or the domains become just the brains on a stick for the computer scientists, but really working together on how these fields can evolve. I think that is a very, very important thing. Ultimately, AI has to be like reading and writing. It has to be something that every domain person understands.
Any other questions at all? Okay, people might want to save that for the intimate coffee and scones I can see over there afterwards. It is really interesting because, I mean, I was having conversations in the pre-meeting here around where it's being accepted and encouraged and where actually resistance is being seen. And it's interesting, even in the medical space, where actually you can see that it's adding value, but even some of the most educated are actually resistant to it. So the challenges that it presents, and I think this gets back to your point about interdisciplinary, I don't think it can be underestimated because people are sometimes fearful of this or what's it going to do to their role, even though it actually adds value and perhaps helps in that predictive capacity. I think it's really interesting. To close, I'm actually going to ask Professor Michael Bruni to come and give a vote of thanks so that when you can move on to informal networking. Thank you.
I wasn't really prepared for a vote of thanks, Peter, so you're dubbing me in here. I think we heard a fantastic talk from Vishal. It's an absolute pleasure to have him here and talking about the 5 points. I think many of us were just taking down notes and saying, okay, going to remember those 5 points. As an Australian, I'm always worried about the asymmetry that you were talking about. You mentioned the US and China quite a bit in there, and it scares a lot of us thinking that this is where the $34 million can be invested in training a 500 billion parameter model. We have none of those companies genuinely in Australia operating like that. That's a scary part for us to think about, but it's great to have people like you coming to us and telling us about it. Thank you very much.